All right, hi class. So we're moving on to this chapter, chapter 9. What this chapter is all about is discrete events, and we want to be able to count them and talk about what are the likelihoods of those things happening. It is following from what we learned with set theory, so we're going to use that language and that terminology, and then we're going to talk about how to count the things, the amount of things in a set, and then calculate like the probability of stuff happening. And this is very important in computer science because, everything in computers are a finite length. So they have finite number of things and we can count them. We want to know the probability of things happening, like things going wrong or passwords working or not working, etc. So a really just a basic idea about what probability is just, you have some event and you want to ask yourself how many ways can that happen and what's the likelihood and all those things. Imagine if you had two coins, you could flip two coins and you can just ask yourself, okay, how many heads did I have? Did I have zero, one, or two? And you can imagine that, you flip it for 50 times and then you would count, okay, when I flip the two coins, the two quarters, how many heads came up? And this was from actual data that was run by the authors of the book and they calculated how much they have. So two heads that came up 11 times, one head came up 27 times, and zero heads came up 12 times. Because when you flip a coin, you could have head head, or you could have tail head, or you could have tail tail, or you could have head tail. And so this case there's zero heads, this case there's one head, this case there's one head, in this case there's two heads. So those are the different possibilities that we have over here. Okay, so when we want to talk about this more general, we use this thing called a random event or a random variable or a random process, and we talk about the probability. So random has a very special meaning in math, but it kind of just means what you think it kind of means, which is stuff that happens according either all equally likely or just something that is not deterministic, like I know every single time it's going to come out this way. So that's what we mean by random. So more terminology, the sample space is just the all possible outcomes that we have, okay? And it is a set, so we're going to be using, set notation that we learned previously. An event is just, more definition, it's just a subset of that sample space, okay? Typically, the sample space we call like S, so it's the set of all outcomes, and E will just be a subset of S, okay? Because E is an event. But it is a subset of the sample space of S. Okay. So when we have everything when every single outcome, uh, so say we have a sample space, like say flipping a coin and it's 50-50, heads or tails. If all outcomes are equally likely, then for any sub set, any event, the probability of that event is just going to be you count the number of ways E could happen, and then you count the total number of outcomes in S. So this is under the assumption, assuming all events in S are equally likely. Now, this is pretty much the only type of probability we're going to be talking about in this video, but there are many other types of probability where things are not equally likely. What we're doing is actually called a uniform distribution. It's the technical term. But anyways, for these simple cases we're going to work through, we're going to be assuming this, that the probability of any event is just the number of outcomes in that event divided by the total number of outcomes in the sample space. Okay, some more notation. When we have a finite set, NA just means the number of elements of A. So for instance, if I chose a random number between 1 and 10, there would be 10 possible things. So N of A there would be 10. Um, using this notation to express this law, the probability of E, we would just say it's the number of the events in E divided by the number of events in the total sample space. Okay, or not events, but objects, excuse me. Okay, so just number of uh, objects in E divided by number of objects in the whole sample space. Okay, and again, this is under the assumption, equally likely. All are equally likely. So it's kind of like called like the naive probability, where it's just we assume, okay, they're all equally likely. As a real quick example, I don't play cards, but it's really helpful to learn probability. So a card, in case you don't, a card deck has, in case you don't know, it's all right if you don't know, it has 52 cards and there are four suits. There are two red suits, diamonds and hearts, and there are two black suits. This is called a spade, and that's called a club. Actually, I had that backwards. Sorry. That's a club. It shows you how little I play cards. So spade. Oh yeah, I have it written right there anyways. Okay, so anyways, there are 13 cards going from 2 up to 10 the numbers, and then there's the four face cards, Jack, Queen, King, and Ace. In some games, Ace is considered one, but anyways, the Jack, Queen, King are called the face cards. Okay, so let's imagine that we've shuffled the deck enough, and so we pick one at random. So let's work through this. So the question is imagining what if we have shuffled the deck enough, and so it's thoroughly mixed. That means everything is equally likely. So all are equally likely. That's what that means. Okay, so just imagine we've shuffled it enough. It turns out mathematicians have figured out that you need to roughly shuffle a deck about 7 times to make it completely, random enough. All right. Well, anyways, so you spread them out face down. So we have all 52 possible cards. All right. And it's asking what's we pick one. Well, anyways, part A says, what's the sample space of outcomes? Well, these are just all the cards. I should say every single card because we're choosing one because it says we're picking one card. So the sample space would just be all cards, all single cards like that. So, you could write it out. It would be like the ace of hearts, ace of spades, yada, yada, yada. And you would just go all the way up to, the king of clubs and king of diamonds or whatever, however you want to list it out. Okay. But the number here would just be 52 because we have 52 possible cards. Okay. I don't want to write them all out, but you get the idea. There's a lot of them. So part B asks, though, a more interesting question. What's the event that the chosen card, so again, we're only choosing one, and we chose one at random, what that is a black face card? Well, so to do that, we would say E is the set of all black face cards. Okay, let's write out what that is. Well, that would be, there's only two black suits. So there's the club and the spade, and the face cards are the jack, queen, and king. Oops, hold on. Okay, go away, go away. All right. So it would just be like, the black jack, oh, sorry, not black, club, jack. Hold on. Make sure this is working okay. All right, we're back. I was having a little issue with the Zoom sharing thing. Hopefully it's okay. Well, anyways, you just write out all the different black face cards we have. So we have Club Jack, we have the Club Queen, etc. If you list them all out, turns out you get 6 of them because there are three. There's a Jack, Queen, and King of the clubs, and the Jack, the Queen, and the King of the spades. And I can't really write it out nicely, but anyways, their number of that would be 6. So you just listen to what I said verbally and write that out if you need to. So part C is what is the probability that when we choose one random card, we get a black face card? Well, the probability, since they're all equally likely of that event, okay, would just be the number of the events divided by the number of the in the sample space. So we just take our answers from before, so 6 over 52. Okay. a little more than 10%. I had the number around here somewhere. Yeah, it's roughly equal to 11.5%. Okay, but again, this was assuming that we've shuffled the deck and they're all equally likely, which we're going to assume in most of our these problems on this video today. Okay, so for this example, again, another good one besides cards is dice. And if we roll two die, we can kind of imagine that if we color them different, it's easier to see. And if we roll two die, we can count the number on each die, which the book helpfully calls us, lets us know it's called pips. But anyways, so how do, so we can use this to help us, come solve a problem. So for part A, what would the space look like in this compact notation? Meaning, uh, I've using this compact notation, and the sample space here would be all two die rolls, right? So I just save room and time. It's like it takes a lot to write, okay, but you could, just so you understand what this means, we would write this as 2, 4. So the notation 2, 4, it's not the number 24, but it's just the notation. Well, anyways, I wrote it all out here. So this is what you get if you were writing them all out. So this would be like 1, 1, each die is 1. This random one, like 3, 1, would say the blue one is 3 and the gray one was 1, okay, etc. All right. So I already had the answer here. It's kind of annoying, but for part B, let's write the event where the numbers showing up have a sum of 6. Okay, well, let's just figure out how they would have to add up to 6. Well, five, that one's going to add up to 6. That one's going to add up to 6. That one's going to add up to 6. You kind of get the idea. And then that one. All right, 1, 2, 3, 4, 5. Did I get them all? I did. I got them all. Okay, cool. So that using set notation, that's what is how we would write it. We would say, okay, well, we just write these specific outcomes in a set notation. Okay, and obviously I could ask the probability, what would the probability of E be? Well, that would just be the number of E divided by the number of S. There are 5 that we counted here, 5 objects in E, and I didn't count out what the numbers in S are, but there's 36 uh, in, I should say, uh, 36 in S there, so that would be 5 over 36. Okay. So again, how we kind of, to do probability, we kind of need to be able to count. So how are we going to do that? Well, we're going to learn how to count in a lot of different ways in this chapter, but the simplest one is, say we're counting the elements of a list. You might think this is really simple, but if I asked you how many things, are in this list, it's very easy to make a simple mistake. Now, if you write them all out, it's really easy. So if I say, okay, between 5 and 12, and they just go up by 1, then you just count them and you get 8. Okay? But that is a general principle. Sorry, my screen is messing up again. Okay, so that is a general principle, which is that if you have a list of M and N integers, so between M and we want to include M and N, then the actual formula is not, it's a little bit weird. It's not strictly N minus M, it's M minus M plus 1. So as an example, if I would say, Steph Curry has played, um, you know, since I'm gonna actually have to improvise here. I don't know the exact number. Let me look it up. What was his first season here? So that was the 2009 season. Okay. And right now it's 2025. Okay. So how many years has he played? So how many seasons? Well, then you would just take 2025 you would subtract 2009. Now, you might think naively that would be the answer. So 2025 minus 2009, and that would be what? Um, 16, right? But the answer is actually 17 because you need to add 1. So it'd be minus 16 plus 1, which is 17 seasons. And the reason we add 1 is that we have to count that first season that he was, well, it depends on how you think about it, but we have to count either the first season or the last season. And so if you subtract, you're kind of missing one of them. Okay, and then I can go ahead and count on on the basketball reference, and yep, it's exactly 17 years. He's in his 17th season. So if you forget to add this plus 1, you're kind of like not counting. It depends on how you look at it, the first or the last. So that's kind of a interesting way to, or you might not have ever thought about that, or maybe just do it intuitively. But if I'm trying to figure out the number of things in a list, it's not the simple difference. I have to add 1. Okay. So for part A, how many three-digit integers ranging from 100 to 909 are divisible by 5? Okay. And then we can talk about the probability as well. I think I included a little helpful thing here. Yes, I did. Okay. All right. Oops, sorry. All right. So how many three-digit integers are going to be divisible by 5? Well, we want to count. Okay. I want to start. Obviously, 100 is divisible by 5. So I could sit here and I could count 100, 105, 110, 115, yada, yada, yada. Okay. And I can go forever. All right. Or I can think about it a little more systematically here. I know if I start counting that the only way you can be divisible by 5 is you can say, okay, the last number here has to be 0 or the last number here has to be 5. And how many of those do I have? Well, I would have to go, there would be 20 of these in the 100s places because it goes up to 200, or excuse me, 195. This is like the 0th one or the first one, and then you go up and you get 20 of them all the way up to 195. Okay, and then you do the same thing for 200, 205, yada, yada, yada. Okay, up to 295. Well, how many are here? Like I said, there was 20. How many here? There are 20. And then how many do I have between 100 and 900? Well, I have 9 of them. So it'd be times 20 and it would be 9 of these. Okay? And so the answer here would just be 9 times 20, which is 180. If that was a little too hard, you can also just split up into little sections and then, so say how many between 100 and 105? Well, there's 2. And then how many ways can I get, this is a count of 10, and how many counts of 10 are from 199? And that would be 90, and so you get 2 times 90 is 180, same thing. All right, so for part B, so let's call that an event, so let's call that E here. And then, so that means the number of E is 180. And so if I want the probability of E, that would be the number of E divided by the number of S. So that would be 180. Well, now the question is, and how we're going to use that formula from before, how do I count the number of three-digit integers between, so so now I need to know total number of integers between 100 and 99. Well, that would just be 999 minus 100, but I have to add 1. Okay? And so that is 180 divided by 99 plus 1, which is 180 over 100. Sorry. Uh, that is wrong. 899. Lol. Okay. So 900. And that's exactly equal to 1/5, which is 0.2. So here I had to use that idea that I'm counting in this list. I need to make sure I add that 1 there to make sure I get it right. Okay. Which is also equal to 20%, however you want to describe it. When you're given your answers on your homework, I don't care either way. If you have the fraction, the decimal, or the percent, that's all fine for me. All right, moving on. That was kind of like just a warm-up section. We're going to get into some formulas here. So we want to learn some rules in this section, which are about multiplication rule. let's jump right into it. So say we have these two teams and we want them to play repeatedly until one wins two games in a row or a total of three games. Okay, so the way you win this tournament is you have to win twice in a row or you win three games. So obviously it'd be 3 out of 5 games. So, well, jumping ahead, but so we can denote it like this, and let's say, well, how many ways can the tournament be played? Meaning, like, what are the different matchups? You know, Team A wins first, then Team B, blah blah blah. Or if Team A wins twice, this tournament's over, right? So you can write that tree out, and it's really helpful. So you say the start, then you just make a choice. Okay, which team won? So in this case, Team A won. Now from this vertex, you know, which team won? If A won twice in a row, like on this little branch there, then that means the tournament's over. Okay, so because A won the whole tournament. Okay, and in this note in this tree, in parentheses, just means that that team won the tournament. So say parentheses mean A wins means A won the whole tournament. So this actually here is one event. This is how this tournament went. It was just two games. If I follow along on a different branch, it could be like all the way here. So say team A won, but then team B won. But then hey, team B won. Guess what? That's the end of that tournament. Okay. So B won that tournament completely. And I can go on, you know, if I go B, then A, if they keep flip-flopping like this, it goes really long. Okay, but then boom, that's the end of that one. So that's another tournament, another way that tournament ran. So obviously, part A is asking, you know, how many ways can this tournament be played? Well, so number of, let me use a different color. So number of tournaments, so number of ways can be played. Well, just count the ends of the leaves, you know, on this little tree here. And that's going to be, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10. So for part A, this was asking how many different tournaments do we have? Well, we had these 10 different ways that we got a winner on the tournament. Part B, sorry, I should have copied the question down. Part B says, well, assuming that they're all equally likely, what's the probability that 5 games are needed to be determined the tournament winner? Okay. So for part B, what's the probability that 5 games are needed? Well, assuming they're all equally likely, we just count up the number of 5 games divided by 10 because 10 was the number of the sample space. Okay, we just count here on our tree here for the how many of these had 5 games. Okay, well, obviously it's not going to be this one because this was 1, 2 games. This was 1, 2 games. So we go on. So cross those out. Okay, and if we go here, we have 1 game, 2 games, 3 games. Okay, cross that out. Same deal here. 1, 2, 3 games. Cross that out. Okay, and looks like here are the. Oh, I actually even have it nicely for you. Okay, 5 games. Well, anyways, you could have counted out as well, and you get down to 4. So there are only 4 of those, so the answer is 4 out of 10, which is 0.4, which is 40%. And again, for probabilities, I don't care how you write it. You can write the fraction, the decimal, or the percent. All right. So I kind of like drawing trees on the homework. I asked you to, you know, do that sometimes. It is simpler to be able to, if you can, visualize it, you know, anytime you can, try to visualize something. All right, moving on here. Okay, so the multiplication rule is a real fundamental idea. What it tells us is that if you, let's take this example. So say you have a computer installation, okay, and there are all these different options for what a student, sorry, not a student, what a consumer can buy, okay, and you have 4 different I/O units. That could be like, you know, CD-ROMs or storage drives, SSD or NVMe. You have three different CPUs. Okay. All right. So four and three. So the question is, the overall question is, how many ways can we build this computer in so many words, right? Well, just draw a tree. So if you draw a tree, we first choose what the input output unit is. So say we have A, B, C, D, right? Now these choices are independent. I can choose whatever I want for this IO unit, and then I can choose whatever I want for the CPU. We're assuming that they're all compatible. So if you draw the tree out, okay, for the A thing of the hard drive, then I have three choices then for the CPU. And same thing for hard drive B. Okay, I have three and C and blah blah blah. So if you count all of them up, you get the edge of this tree, and there's 3, 4, 6, 9, 12. So there's going to be 12 um, total ways. And that's what's really cool about trees. If you can draw it out like this, it makes it like really stupidly easy, which is nice. That is a general, drawing this tree is a general application of what's called the multiplication rule. So if you have k steps and each step can be calculated or performed in a certain number of ways, okay, then the tire operation can just is all you do is you just multiply these ways like that. So in this problem, I had four ways and then three ways. So the total number was just 4 times 3. And in the notation, that would be like n1, and that would be like n2. Okay. So let's take a look at that. So we can think about this for passwords too. You can think about it in a lot of ways whenever you have choices to make. Okay. And so say we have your PIN at your bank, okay, and there are 20, we have four, uh, we have to have four parts of the PIN. And for each one, we have 26 choices, okay? So for part A, and it's just saying the uppercase letters, and the 10 digits actually, sorry. So how many do I have total? I have 36 choices for each part of the PIN. So how many different pins are possible? Well, they're saying that, okay, you just each one you're allowed to have 36 choices. So it'd be like I have 36 here, I have 36 here, I have 36 here, and I have 36 here. So the answer here would just be 36 to the fourth, like that. That's the total number of possible choices. And I think I have a picture here for you. Yeah. Again, I just have 36 choices in each box, and so the total number would be 36 raised to the fourth, which I think I've calculated somewhere here, which is going to equal 1,679, oops, 679,616. So lots of pins when you only have just a four-digit thing, which is pretty cool. So part B asks, now how many different pins are possible if you're not allowed to repeat a symbol? And so you can imagine building a little checker in your programming to make sure that, okay, if the first digit was, B or 3, you throw out that possibility. Well, again, you still have four things you need to fill. The thing is, though, is that when you're free to choose from all 36 here, but say I chose the letter F, I can't choose F again. So now in this box, how many am I allowed to choose? Well, I have one less, so that's 35. So say I chose the number 2. Well, now I can't choose F or 2. So now I have how many? I have 34 left, and vice versa. And because, each one is allowed to happen separately, then you just say the total ways would just be, you multiply them. Just 36, 35, 34, 33. And I calculated that earlier, which, yeah, is 1,413,720. So significantly less, like 200,000 less, 270,000 or something like that. Okay. Now, part C is what's the probability that a pin does not have a repeated symbol? Okay. Well, that would be, so probability of, let me give it a name. So let's say E is no repeated symbol. Okay. S obviously would be all pins. And so we know from the naive probability rule that the probability of E, since they're all equally likely, is just the number of E divided by the number of S. And we calculate that. So over here, this was the number of no repeats. Okay, so it was 1, 4, 1, 3, 7, 20. And the number of before was the big number, the all possible. Okay, and I've roughly done this already, so it's 0.8417 or 84.17%. And these are estimates. It's the decimal goes on a long time. Okay, so roughly 84% of pins would not have a repeat this symbol. Okay. All right, moving on. Kind of moving on quickly because I want to get through this. There's a lot of material here. Almost done with this section though. So the last little thing here is about permutations. Okay, what is a permutation? Well, say we have it's just an ordering of all the objects. So for instance, if I'm choosing the letters A, B, and C, what are all the ways I can order it? Well, I can go A, B, C, I can go A, C, B, blah, blah, blah. Okay, and turns out there's exactly six here. So there's six, and we would call that permutations of, and you can even write it into the set notation of A, B, C, like that. Now, the question we obviously want to ask is, given a set of n objects, how many permutations do I have? Uh, well, for instance, this one, let's think about it. Let's again choose the boxes and do the multiplication rule. For this first box, how many letters do I get to choose here? Well, I have three choices. I have A, B, or C, right? Now over here, I've already chosen A. How many letters do I have to choose for here? I'd only have to be able to choose B or C, so I only have two ways there. And since I've chosen A, B, and B, I'm only allowed this last one to be C. Okay? And that just means that the number then, I should say, the number here by the multiplication rule would be 3 times 2 times 1. Okay? I should say number of possibilities or whatever of permutations. And that's just 6. Now, this comes up so much that if we have, say, a set of n things like A, B, C, dot, 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 up to n things, okay, and call that event E here. So if I want to know the permutations on E, well, that would just be, that would just be the number of things in there. So I would have n choices for the first box, and then n minus 1 choices for the second box, and n minus 2. Anyways, this has a number or a symbol attached to it. This is called n factorial. So factorial. And that's what this box here says, okay? The permutations of a set with n elements is n factorial, okay? And just so you have some examples, okay? 5 factorial, that's 5 times 4 times 3 times 2 times 1, which is going to be 120. It's quite large. Okay. 2 factorial is 2 times 1, which is a 2. Okay. And, 1 factorial, that's just 1 times itself, which is 1. We need, just so you know, okay, make a big note to yourself. Okay, it doesn't make any sense. Okay, but 0 factorial, it doesn't make any sense. Like there should be no answer here, but we are to make it helpful for many formulas. We just call it 1. Okay. So note by convenience or by, I don't know how you want to say it, by convention, we define 0 factorial as 1. Doesn't make any sense. It doesn't match this definition, but whatever. In this definition, this theorem, it actually says, well, let's just let n start at 1, but we do need 0 factorial to be 1 as well. Okay, so here for A here, how many ways can we arrange the letters in the word computer? Well, let's just count how many letters we have. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 letters. So that tells me that n is equal to 8. And so the permutation there would just be 8 factorial, which is really huge. I don't think I even have that number memorized. Luckily, I have it here, 40,320. It's huge. Part B asks how many ways can we arrange it if we have to chunk the CEO together, okay, in order as a unit. Well, you might think, man, it's kind of hard what to do, but just remember that just this means that this think of this as a letter. So now CO itself is a letter. How many letters do I have? Well, I have just one, but then I have two, three, four, five, six, seven. So I have seven now. So N now is seven, uh, is seven. And so it just would be 7 factorial, which would be 5040, like that. Okay, so it's like we chunked this together, and so now we removed one of the letters because we combined C and O. C asked, what if the computer are randomly arranged in a row? What is the probability that the letters CO remain next to each other in order as a unit? Okay, well, what this is really saying is, so say, let me call that the E is that event, okay? So CO remain together, okay? S is total ways to permute computer. Well, we've actually found this now. So this was earlier, this is N of S, okay? And this over here is N of E. Okay, so assuming the naive probability thing, we know that the probability of E is just the N of E divided by N of S, which would be 5040 over 40,320. And that actually is an exact answer. It's 1 over 8, which is cool, and that's 12.5%. Okay, cool. All right. So moving on here, and sorry for moving fast. Remember, you can pause the video and stuff like that. One last little thing we want to talk about is what are called the permutations of selected elements. So that just means that, hey, we want to kind of glue some things together, or we want to pick, say we have a set here, A, B, C. What if I don't want the whole thing? I don't want to arrange all A, B, C. What if I just want to have all the different ways to arrange like a two-letter version of that? So from this set of N things, I want, I want to permute R of them. Okay, so we call that an R permutation. Okay, we denote it as P and R, or you might hear me say permute. You might hear me say N permute R. That's another way we say it. Okay, it just means the number of subsets, or the number of things where I have R elements from N. Okay, turns out it has this really nice formula. Okay, I don't really not in the mood to prove it. Actually, we would need induction, which we not necessarily have just yet in the order that I've done so far this semester. So the proof would require some stuff that we don't have just yet. But anyways, I just want to use it to be able to calculate some numbers. So here, evaluate P52. So that's 5 permute 2. Well, according to the formula, this is going to be my N, this is going to be my R. And so this is going to equal 5 factorial over 5 minus 2 factorial. Okay. And do I have the numbers ahead of time? Yeah, okay. Well, this is 120 over 3, which is 6. So it's 20. So 120 over 6, which is 20. You can use your calculator to do factorial, or you can write it all out if you're not sure why that is. Okay, 5 factorial is 5 times 4 times 3 times 2 times 1. 5 minus 2 is 3, and 3 factorial is, uh, sorry, is 3 times 2 times 1. And you can see that these cancel out. I hate this app. That cancels out with that. Anyways, you get the idea. Okay, and so you're left with 5 times 4, which is 20. Or you can use a scientific calculator or a graphing calculator to do permutation as well. Okay, part B asked, how many 4 permutations are there of a set of 7 objects? Well, again, this is R here, and this is N, and so it's really just saying 5, 7 permute 4. which you just plug into the formula and you get the idea, which is 7 factorial over 3 factorial. Okay. And this is 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 3 times 2 times 1. And you can see what part cancels out, and you're just left with that, which equals 804. All right. And last little bit here. This is asking how many 5 permutations there are. So R is 5 and N is 5. And that just means 5 permute 5. Well, that's just like the example we did with A, B, and C. We want actually all of these. So this is just going to be, I know this is going to be 5 factorial. But let's see. So this is going to be 5 factorial, 5 minus 5 factorial. Now this is, according to the formula, we need to do that. And we get 5 factorial over 0 factorial. Uh-oh, I'm dividing by 0. Well, thank God we defined by convention that 0 factorial is 1. So this is just 5 factorial over 1, which is just 5 factorial, which is 120. So you can kind of see why we define 0 factorial as 1. All right. I think that is a good place to stop. I'll split this video up into the next section. Okay, so we just have one more section uh, for these set of notes, and I'll post that as part 2 of this video. So part 2 coming up. All right, thanks. See you on the next video.